So we're talking about Moore's law for this discussion board. And the basic idea is that Moore's law is, it's actually right here, it's saying that the progress of technology can be measured to double every 2 years. So we're going to see and make some hypotheses about that in the specific example of transistors. So the number of transistors on an integrated circuit chip, which is something that's not my area of expertise, but we can deal with at least the numbers of the circuit on the circuit chips. Look, usually on the y-axis we increment by the same amount each time. We keep it linear: 1,000, 2,000, 3,000, 4,000. But the y-axis, the number of transistors on an integrated circuit chip goes up by 1,000, then 5,000, then 50,000. So what they've done is they've changed the increments for the y-axis, and that makes it more suitable for looking at a logarithmic scale. Like right now, as I make this video, we're seeing logarithmic scales for tracking the disease outbreak. So you can hopefully see a linear pattern because it increases exponentially. One person has it, then 2, then 4, then 8, and increases at a faster and faster rate. So that's what's going on with the graph here. For part A, the number of transistors per integrated chip, or whatever that abbreviation was, in 1972 seems to be about 4,000 for a starting amount. Okay, so they used a rough eye estimate to make that, and I kind of got misled. I thought for the prediction they wanted us to do another rough eye estimate. But what actually they want us to do is to use Moore's law in a type of function setting. So let's get some pencil and paper out. For me, it's a little whiteboard. Moore's law says that things double every 2 years, right? So if we got 4,000, then after 2 years, so 1974, we should double, right? 4,000 after 4 years, we should double that double. We should multiply by another 2. And then after 6 years, we're multiplying by 3 of these 2's. So another way of saying this, it's 4,000 times 2 to the first. This is 4,000 times 2 to the second. This is 4,000 times 2 to the third. And we just want to keep in mind that this is when we've gone, this is at 0 years. This is when we've gone 2 years. So we don't want to put t equals 1 here. This is when t equals 3. This is what we should be getting out. So if you notice, every time we go 2 years, we increment the power of 2. We increase it by 1. So for Moore's law, what you need to do is come up with a function that predicts based on time the amount that we have, the amount of chips we have per IC. So it said we start off, at least for mine, it said we start off with 4,000. That would be your A in your exponential function. B, I'm just going to give it away here. I'm not going to give away all the parts of the discussion board, but B is going to be 2 because that's our rate of growth. So you can plug in 2 here, or there are other ways of modifying it, but we can all plug in 2 for B if we're having trouble. Now, the exponent part up here, this is where you're going to have to plug t, but it's not going to be just t. You need to do something to it. You got to either multiply or divide by something, because it's not every year that this thing doubles, right? It's every 2 years that it doubles. So how could you take an expression for time and make sure that whatever comes out of the expression, it's been cut in half? There's a couple of different ways you could write it. Both would be equivalent. So you need to do something to this t, and then try out your function. Make sure that whenever you plug in a year for t, it's going to spit out like 2, 4, 6, or something like that. Okay. I guess maybe one other hint just to make sure students don't get lost there. Your function doesn't look like this, okay? 4,000 is good. That's how much we start with. If we're going to use 2 for our base, this wouldn't be correct. Because if you plug in 1, if you want to find out like how many chips are after 1 year, then we're going to be doubling it 4 times, right? Because 2 times 1 makes 2. 2 to the 4th makes 4. So that's no good. So multiplying by 2 isn't what we need to do. You need to do something to that variable t. If you're still having trouble, you can message me. I don't want you to stress about the discussion board. I can give it away if you just email me. I'd like you to try first, because otherwise the students can just sign in, just take the exact same function. But give it a try. If you're still stuck, email me and I'll show you what you need to do to finish that out. Because once you have that function, all you have to do is plug in 20 for t, because it's saying 20 years later. So plug in t equals 20 into the function. Once you've constructed this function, all you have to do to make a prediction is plug in 20. For part B, for the chart, from the chart, estimate the number of transistors per IC in 2018. So this is where you can make your own estimate. Look, it's not even having you plug anything. This is where we don't use a function. We want to estimate from the chart the number of transistors per IC in 2018. So go to 2018 and then find out where that might cross the y-axis according to the trend that we're seeing here. So try to find out what the y value is, not the logarithmic value, but this value here, the number of transistors when x equals 2018. And part C is largely opinion-based. Do you think this is believable? You know, the big thing with mathematics and statistics, and the way it gets abused, is when we try to make predictions into the future. Okay, it happens all the time. You know, we come up with this really great model that represents historical data, and it does a really good job of predicting values in between our data set, but then it does a really bad job of predicting the future because, well, technology is still pretty relatively new territory for human growth. There's a lot of reasons why it might be tough to predict. If you have some insider knowledge on these transistors, you probably know more than I do because that's not my field. Maybe you can say, yes, I believe Moore's law is still going to apply. Okay, so that's everything. The big part here is creating that function. Just let me know if you don't know what to put in the exponent to finish that off, okay? Because once you have it, you're going to plug 20 in for t. So this is supposed to be t, but with some sort of modification. You need to change that part. Then once you have it, you plug 20 in for t and simplify.